Good morning, my name is Jordan. I will be presenting my FYP titled Microstructural Evolution of Solder and Silver Sintered Die Attach under Thermal Aging for EV Power Modules. Today, electrical vehicles adoption rate is growing rapidly. It requires to push power electronics to operate at higher voltages and higher temperature than ever before. As a result, ensuring the long-term reliability of EV power module has become a critical challenge. In high voltage EV power modules, devices are exposed to high temperature, severe thermal cycling, and electrical stress. With the transition from conventional silicon devices to silicon carbide and gallium nitride, which operates at higher junction temperatures approaching 175 to 200 degrees Celsius, while also delivering higher power density and faster switching frequency. Although these wide bandgap devices can tolerate such conditions, the packaging materials often cannot. As a result, reliability bottleneck shifts from device to packaging, particularly the die attach layer, which is responsible for both mechanical support and heat dissipation. So, what is failing? Conventional solder-based die-attach materials were originally developed for lower temperature silicon devices. Under the elevated operating conditions of EV power modules, these solder joints degrade due to crack deformation, thermomechanical fatigue, and especially intermetallic compound growth at the solder-copper interface. During thermal aging, brittle copper thins IMC layers grow and promotes crack. This leads to crack initiation and propagation, followed by interfacial delamination, which disrupts heat flow, increases thermal resistance, and ultimately causes localized overheating and device failure. To address this reliability issue, this study has three objectives. Firstly, to establish the relationship between die-attached material used in silicon carbide power module. Secondly, to investigate microstructural evolution of silver-sintered die attached under thermal aging. And lastly, to compare microstructural stability and thermal performance. To achieve these objectives, this project compares conventional solder die attach with silver sintered die attach, which is increasingly adopted in advanced power module packaging. Silver sintering is attractive because it offers higher thermal conductivity and higher operating temperature capability, as well as avoids the formation of IMC. Thermal aging will be conducted under EV-relevant conditions, and microstructural characterization will be performed using SEM, EBS, and XRD, focusing on grain growth, crack propagation, and interface integrity. At the current stage of the project, preliminary findings are based on reference material data and reported studies. EDX reference data confirms a clear compositional differences between solder-based and silver-sintered die attach, while material property mismatch such as CTE and thermal conductivity suggest high thermomechanical stress during operation. Literature consistently shows that solder joints suffers from grain coarsening and intermetallic compound growth, whereas silver-sintered joints exhibit more stable microstructure without thick brittle IMC layers. These findings strongly support the research direction and motivate further experimental validation. In the next stage of the project, samples will be fabricated and thermally aged at 175 degrees Celsius for 250, 500, and 750 hours, followed by detailed microstructural analysis. The outcome will be a quantitative reliability comparison, directly supporting material selection for high-temperature EV power module packaging. Ultimately, this project aims to contribute towards more reliable and thermally robust EV powered electronics. Thank you.